So in the last chapter, whatever we studied is depicted in figure 3.7. So we studied about various strengths and physical properties of all the elements, and in that we studied about the atomic radius, we studied about the ionic radius, electronegativity, electron gain enthalpy, ionization enthalpy. So, and also we talked about the metallic character and non-metallic character. I hope that it is understood. It is clear to everyone. And then now, if that's so let us go ahead with the chemical properties. So now we will be seeing the periodic trends in the chemical properties. Again, there has to be some trends in the periodic table, because periodic table is arranged in such a way that it has to have some trend. So most of the trends in chemical properties of elements, such as the diagonal relationship, inert pair effect, effects of lanthanoid contraction, etc., will be dealt with along the discussion of each group in later units. So what chemical properties we will be dealing is the diagonal relationship, inert pair effect, and the lanthanoid contraction. Okay, so so we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period element from lithium to fluorine. So obviously in the periodic table also, when I am saying a line that electron gain enthalpy increases when you go from left to right. So even I'm saying this point is not rigid. It actually is not rigid. There is some anomaly and there has to be some exceptions. So, so it is not that. If I'm saying that from going down the group, yeah, some properties of some property like physical property per se is increasing. So it doesn't mean that it will increase for every group. So there are some anomaly, and there has to be some exceptions, and that exceptions also we need to learn because those are important. So let us start with the periodicity of valence or the oxidation states. So what are different oxidation states? All the group elements or the period elements are, we'll see. Generally, we see all of these group wise, okay? So the valence is the most characteristic property of the element and can be understood in terms of their electronic configuration. Actually, all the properties you can, identify on the basis of their electronic configuration. So valence is also one of them. So valence in the sense that what oxidation state it will show. Okay, so it depends upon the electronic configuration again. So the valence of representative elements is usually equal to the number of electrons in the outermost orbital or equal to 8 minus the number of outermost electrons as shown below. So you need to learn this. So how, like, number of electrons any molecule has in its outermost orbital, those are only the electrons that are available to be lost, right? And so that will be the oxidation state in the positive form, because you're losing electron, and you have oxidation state in the negative charge also. So in that case, 8 minus the number of electrons, so that we know that in order to complete octet, you should have 8 electrons in the valence shell, right? So if you need to incorporate some electron to make it 8, so how many number of electron you will put to an element to make it 8? So that will be equal to 8 minus the number of elements already present in the valence shell. So that is what is written over here. So nowadays the term oxidation state is frequently used for valence. Consider the two oxygen containing compounds. We are talking about OF2 and Na2O. So we are considering these two. So the order of electronegativity of the three elements involved in this compound has to be fluorine is the most electronegative, then oxygen, and then nitrogen. Sorry, not nitrogen, sodium. So it is in the order. F is the most electronegative, then comes oxygen, and then comes sodium. Sodium is the least electronegative. Actually, I would say that it is electropositive in nature, because it doesn't has the tendency to accept electron. It has the tendency to give electron because it is metal. Okay, metals are electropositive. So this is the electronegativity pattern of the elements involved in this question. So when we are talking about OF2, okay, since F is more electronegative, so it will carry negative charge in itself, and oxygen will carry positive charge. Here with oxygen there is nothing, so that means it is 1. So you can write it as O, 2 positive, F negative. Okay, so this 2 is because of the oxygen. This one is because of the fluorine, and the negative charge will be there in that atom, which is more electronegative. So now consider Na2. Oh, okay. So here most electronegative is oxygen, and this 2 is for oxygen. So first of all, you need to have negative, okay, and for sodium you need to have positive. Now see, this 2 has to be for oxygen, so this 2 will go here, and there is 1 here, so this 1 is for the sodium. So these are the various oxidation state. I hope that I'm clear with whatever I'm writing. So what is the oxidation state of oxygen in OF2? It is O positive, O2 positive. And what is the oxidation of oxygen in Na2O? It is O2 negative. Okay. So let us see what is written. If you read it, it is actually same. So you will understand. So let us read on also. Each of the atoms of fluorine with outer electronic configuration. So you should also know the electronic configuration of fluorine beforehand. So fluorine is 2s2 2p5. Okay, it is group 17 element. Okay, so and shares one electron with oxygen. In the OF2 molecule, only one is there, so it shares one electron. So being highest electronegative element, fluorine has given oxidation state of -1. There are 2 fluorine atoms in this molecule. So oxygen with outermost configuration is this. So two electron is given to by fluorine to oxygen. Okay, so it is oxygen is accepting. So she has 2 electron with fluorine atoms. Okay, fine. So F is more electronegative. So who wants electron? F wants electron, right? So and oxygen is 2s2 2p4. So when oxygen is giving one electron to each fluorine, so now it is becoming 2 electron deficient. So oxygen is 2 electron deficient means oxygen is +2. Okay, so similar way Na2O. So and also you will you read and you understand. So it is just the same way. So problem 3.8, using the periodic table, predict the formulas of compound which might be formed by the following pair of elements: silicon and bromine, aluminum and sulfur. Very good. So now let us first do question number 8. So silicon and bromine. Okay. Silicon, I'm writing it over here. Bromine, I'm writing it over here. Okay. So first of all, you need to know what is the electronegativity. So which is more electronegative? So bromine is more electronegative, or silicon is more electronegative. Like that, you need to decide this. So when we go from left to right in the periodic table, then the electronegativity is increasing, and when we move down the group, then the electronegativity is decreasing. So when you are considering, okay, so before that, let us write the electronic configuration. So for silicon, it is what? 3s2, 3p2. For bromine, it is what? 4s2, 4p5. Now you have to give and take electron, or like yes, give and take electron in such a way that both will have octet. So if now silicon has 2 electrons that it can give, and bromine has only one space left, only one electron. So that means that you need 2 bromine atom, right? So Br2 you need, and there is only one silicon that can give its 2 electron to 2 bromine, and here also the valence shell will complete, and here also it will be 2s2 2p6. So you need two of this to have. So that is why bromine 2 and silicon will be 1. So this is the formula. Okay. But this is not right. So actually here there is valence shell electrons are total of how much valence shell electrons is present. There are 4 and here it is 7. So for 7 to complete 8 it only needs 1, right? So it is better to gain 1 than to lose 7 to become 8. And for 4, in order to complete octet, it needs 4 more electrons. So this also needs electron, this also needs electron, can't be there. So, and also you know that bromine is more electron negative. So out of these two elements, who like which element, which atom is going to take up the electron? That atom will take up the electron that is more electronegative. So bromine will take up an electron, and bromine, one atom of bromine is only one electron to complete the octet, and silicon is can give 4 electrons. So you need bromine 4 and not 2. Okay. Now in similar way, when we are talking about two other elements, that is aluminum and sulfur. Here also it is very easy because sulfur is more electronegative. Aluminum is IUM, that is it is metal, so it is not electronegative. It is actually electropositive. Metals are electropositive elements, and sulfur is a non-metal, so it is electronegative. So for aluminum, the what is the electronic configuration? 3s2 3p1. For sulfur it is 3s2 3p4. Now this has how many electrons in its valence shell? 3. Total you need to count. 3s2 is also valence shell, and here you have 6. Total how many electrons you need in order to complete the valence shell? It needs 2 more electrons, and in order to complete its valence shell also, it needs to give 3 electrons. So how it will form? It will give 3 electrons. It needs 2 electrons. So you can write it as like this. And now you see if I'm right or wrong. So now this can give 3. This can take 2. So in order to make it equal, this number equal, you need to multiply it by 2. You need to multiply this 2 by 3. So that is what is written. You need 2 atoms of aluminum, 3 atoms of silicon to complete this valence shell of both the elements. And that is why this is the formula. I hope I'm clear. Okay. Some periodic trends observed in the valence of elements, that is the hydrides and oxides, are shown in table 3.9. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. So this is table 3.9. This is table 3.9 and it is about the periodic trends in the valence of elements as shown by the formulas of their compounds. So lithium generally give 1 electron and hydride needs 1 electron. So that is why LiH, NaH, KH. Here calcium is +2, has to be +2 because it can give 2 electrons to complete the octet, and hydrogen H minus, H actually, this is 1 electron. So you need 2 electrons in order to take 2 electrons. So that is why it is CaH2. So this is a similar thing that I think you will understand the table likewise. So there are many elements which exhibit variable valence. So this is particularly characteristic of the transition elements and actinoids, which we will study later. So let us study about the anomalous properties of the second period element. First of all, what is the second period element? You need to memorize. So the second period element is from lithium to fluorine. So when we're talking about second period, we don't consider neon because that already has complete valence shell. So 8 octet is already complete. So that we are not considering over here. So we are talking about the anomalous properties of the second period element. So the first element of each of the group 1, that is lithium, 2 beryllium, and groups 13 to 17, boron to fluorine, differs in many respects from the other members of their respective group. For example, Lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, form compounds with pronounced covalent character. Okay, and the other members of this group predominantly form ionic compounds. Because when you go down the group, then the metallic character is increasing, and that is why more ionic bond you're forming. But these two compounds generally form, like lithium and beryllium, they more predominantly form covalent compounds. So in fact, the behavior of lithium and beryllium is more similar with the second element of the following groups, that is magnesium and aluminum respectively. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, that is the next group, that is the magnesium and aluminum respectively. This sort of similarity is commonly referred to as a diagonal relationship in the periodic properties. So it is very, very famous term, the diagonal relationship. There exists diagonal relationship in the periodic table. One of them is right that what we are discussing. So lithium, sodium, beryllium, magnesium, boron, aluminum. So this is group 1, group 2, and this is group 13. So when we are going down the group, like when from lithium to sodium, the ionic character is increasing. From beryllium to magnesium, again ionic character is increasing. But for lithium and beryllium, but magnesium is lesser ionic than sodium is, right? We have already discussed all of this. But lithium and beryllium has pronounced covalent character, okay? And it is seen that lithium doesn't show similarity to that of sodium, instead shows similarity to that of magnesium. And similar, beryllium doesn't show similarity to that of magnesium, but shows similarity to that of aluminum. What is the reason for the different chemical behavior of the first member of the group of elements in the S and P blocks compared to that of the subsequent members in the same group? So this anomalous behavior is attributed to the small size, large charge upon radius ratio, and high electronegativity of the elements. So in addition, the first member of the group has only 4 valence orbitals, that is 2s and 2p, available for bonding, whereas the second member of the groups have 9 valence orbitals, 3s, 3p, and 3d. 3d is also there. As a consequence of this, the maximum covalency of the first member of each group is only 4. Example, boron can only form BF4 negative, whereas the other members of the group can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminum can form AlF6 3 minus. Furthermore, the first member of the P block elements displays greater ability to form p-pi multiple bonds to itself. Like it has a more tendency to form bonds with itself because and to other second period elements only, because they're okay. The reasoning things of this code paragraph we'll be dealing with right now compared to the subsequent members of the same group. So we have seen that the first period. So this period we're talking about the second period, right? So this, or we can say the first element of the P block, Y or the S block. Why they show different behavior than their subsequent elements of the same group? The reason for that is that, first of all, it has only like 2 types of orbitals to be filled, or we can say that it can accommodate only 8 electrons. One is the 2s and another is the 2p. Okay, but for the rest of the elements in that particular group, they have expanded octets, so they have the d orbitals as well to have the electrons. So that is one difference. And also these elements, they are very, very small in nature and also highly electronegative than rest of their counterparts, like rest of the elements in the same group. So that is why because of these two ideas, because of these two reasons, this period 2 elements shows anomalous behavior. Okay, and also for P block, so generally first elements of the P block, they actually tend to make bonds with itself only. Like one carbon will like to make bond with another carbon, not elsewhere. So that is because the orbitals of the first elements of the P block are very, very small. So and the rest and the subsequent down elements, when you go down the group, then the size increases, and also the size of the orbitals also increases. So when you're making bonds, then that means you are actually overlapping the orbitals. So the overlapping of orbitals, one small and one big orbital overlapping, is not that much efficient. So that is why, in order to make stronger bonds that is more energetically stable, it likes to form bonds with the same, like itself. Okay, or the other first p block elements. So are the oxidation state and covalency of aluminum in this same? So let us deal with this question. First of all, you need to know what is the difference between the oxidation state and the covalency. So the oxidation state is the number of electrons it is sharing, and covalency is the number of like um, atoms to which it is attached. So here, aluminum, then we have chlorine, then we have water molecule. We know that water molecule is neutral, right? It is a molecule. And whole charge is 2 positive. So how much charge will water molecule have? It will have 0 charge because it is a molecule. It is not charged species. And then you know that chlorine generally shows 1. So it has a tendency of taking 1 electron and becoming, and its octet will complete. Okay. So it will have -1 charge. And this you need to know. So you know when you add the overall charge inside, then you should have a total of +2 charge outside. Right? So this is the equation that you need to solve, which will give the x as +3. So the oxidation state of aluminum here is +3, but what is the covalency? So aluminum is actually attached to how many atoms? 1 chlorine and 5 water. So that means its covalency is 6. So this is the way you need to deal with all such questions. Now we will be talking about the last topic of this chapter, which is the periodic trends and the chemical reactivities. So we have observed that the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization, enthalpy, electron gain, enthalpy, and balance. So we have already dealt with all these physical properties, right? We know by now that the periodicity is related to the electronic configuration. This is the most important line in this chapter because everything depends upon the electronic configuration. That is how periodic table is made. So that is all the chemical and physical properties are a manifestation of the electronic configuration of the elements. So that is why it is very, very important to learn the electronic configuration. And by classifying this periodic table, it is very, very easy for anyone to tell especially the valence shell electronic configuration of that particular element. So we shall now try to explore the relationship between these fundamental properties of elements with their chemical reactivity. So the atomic and ionic radii, as we know, generally decreases in period from left to right. As a consequence, the ionization enthalpies generally increase. Okay, there is some exceptions. And electron gain enthalpy become more negative across a period. Yes, we have already studied this. So in other words, the ionization enthalpy of the extreme left element in a period is the least, and for that element, the electron gain enthalpy will be the highest, or we can say most negative. Note that noble gases having complete filled shell have rather positive electron gain enthalpy values. Yes, because it doesn't want to give electron, and or definitely it cannot take up electron. That is why it has a positive electron gain enthalpy values. So this result into high chemical reactivity of the two extremes. So when you are in the left side, the most extreme left side, it has the highest electron gain enthalpy, and when you are the most extreme on the right side, then you are the highest ionization enthalpy, and that is why the two extremes of the periodic table, those elements are most reactive. Thus, the maximum chemical reactivity at the extreme, that is left among the alkali metals, is exhibited by the loss of an electron leading to the formation of a cation, and at extreme right among halogens, shown by the gain of electron forming an anion. So this is what we are talking about here. The reason we all know. So this property can be related with the reducing and the oxidizing behavior of the element, which we will learn later. However, there it can. Thus, the metallic character of an element, which is highest at the extreme left, decreases, and the non-metallic character increases when moving from left to right across the period. So, the chemical reactivities of an element can be best shown by its reactions with oxygen and halogen. Here, we shall consider the reaction of an element with oxygen only. We are restricted to oxygen, and we will um, react any element with oxygen, because we know oxygen is on the extreme left side and it is also very reactive. Elements on two extreme of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on the extreme left is most basic. Okay, it is Na2O, because sodium can give one electron, oxygen can take two electrons to form its octet. That is why you need two sodium. So it forms Na2O, whereas that formed by the element on the extreme right is the Cl2O7. Chlorine can, so you need to first decide is on such a basis that which is most electronegative, and that is according to which it will give. So the most electronegative out of the two will take up the electron. Oxides of elements in the center are amphoteric or neutral. Amphoteric oxides behave as acidic with amphoteric oxides behave as acidic with bases and as basic with acidic, whereas neutral oxides have no acidic or basic properties because they are metalloids. That is why their oxides are also both acidic and basic. Acidic and basic means when you react such oxide with water, then it will give base, and when you react this has to be acidic oxide. So then when you react with water, then it will form some acid. So among transition metals, that is the 3D series, the change in atomic radii is much smaller as compared to those of the representative elements across the period. So actually transition series behaves differently, okay, when it comes to the atomic radii, because it has a lot of electrons in its potential, like it can have it has the highest number of electrons and also actinoids and lanthanoids. So there occurs some contraction in the size. So the change in the atomic radii is still smaller among inner transition metals. Yes, since it has more number of electrons. So the ionization enthalpies are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and group 2 metals. So in a group, the increase in the ionic and the atomic radii with increase in the atomic number generally results in a gradual decrease in the ionization enthalpies and regular decrease in the electron gain enthalpies in case of main group elements. Thus, the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and the oxidizing property, which we will learn later. In this case, in the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. As I told you, you can explain everything in terms of ionization enthalpy and or basically I can say atomic size and the electronegativity. So we will be solving the question in the next lecture. I hope the chapter is clear, and after that, while solving the question, it will be more clear.